Uh, Thank you so much. So we have discussed about how BPNN, that is back propagation neural network, can be implemented through the MATLAB coding. So if we applied BPNN on these particular facial expressions, so what we get on a day-to-day basis, the bar chart of how the different emotions are generated, we can got for two different types of the gaming. One is the Candy Crush Saga, that giving us a very positive impact on our brain, whereas Stickman Occurs, where you can understand it's a very much a violent sort of game, lots of blood is there, so it basically giving us lots of negative emotions. And the day, how many number of days we are playing that particular game, based on that you can check if the number of days are increasing, so then more number of negative emotions we are getting over here. So that is the application of AI, where the data has been captured from the images. Next, if the data is being captured from the brain signal, so that is basically the cognitive can be understandable. From the brain signal we can understand how the gaming has impact on our brain. So this work has been done by my master student Sima, where in this paper we have understand, we have tried to develop how mm, uh, AI tools can be applied on the EEG signal, that is electroencephalograph signals. This particular figure you can check. This is the EEG sensor that we have in our lab in the Macaut campus, Horinkata, and this one particular subject is there. So EEG, this EEG can be of two different types. One EEG is the invasive one, another is the non-invasive. So it's very difficult to get the permission to work on invasive ones, and it will be very difficult to get the subject will allow us to implant the EEG electrodes. And this invasive one need to be done always in a proper medical setup. It cannot be done in any engineering labs. So what we have procured a non-invasive one, EEG, from the brain tech system. So this the data has been captured in the brain tech traveler system over here. So there are 21 number of electrodes are present in this particular EEG sensors that we have in our lab. The subject is giving us the EEG while playing the games. So two different types of game has been asked to play by that subject for a longer duration of time, and these 21 electrodes are placed in the brain scalp of that subject. Based on the data is being captured, like whatever with the subject is actually processing in the brain. After uh, recognizing or processing of that particular brain signal, we can say what are the type of emotions that are being generated in the human being. So this particular work, these are the, you can check over here that particular subject in the EEG signals we have. There is 21 EEG electrodes are there. So this is the brain tech traveler system is there, and these are the now EEG signals that we have captured. One particular screenshot of that. This is the brain activity regions for different frequency range, alpha, beta, gamma. Different frequency range are there for the EEG signal. These are the brain maps we have, and this denotes that how many excited. So here you can check this particular region is much more excited from this particular one. So this is the user interface of the brain tech traveler system that we have in our lab. So this particular work that will be implemented in the hands-on session, and that will be demonstrated by my research scholar. She is already doing research under my guidance, and she is getting fellowship from the AICD. Ohuna Ghosh. Ohuna, can you hear me?
Yes, ma'am. Am I audible?
Okay. Yes, you are absolutely audible, and she is going to demonstrate how Python can be implemented. And if you have Python with you, you can try to run the code at hands-on session. So it will be best if you try to run on your own as well. So try to run it, and the codes will be written in the Google Collaboratory. So it will be very easy for you to run the codes. So you can run that particular code with her as well. And if you're facing any difficulty, please let us know. So Ahona, you can continue.
Yes, ma'am. I am presenting my screen. Is the screen visible?
Yes, visible.
Okay. As already discussed by ma'am, we are going to detect emotion while playing some games, and for that we have considered a dataset, game emo dataset, from a very well-known platform called as Kaggle. They're from 28 different subjects. EEG data were acquired, and four different computer games were said to be played by all the subjects, and four different computer games belonged to boring, calm, horror, and funny genre of Play Store. And the EEG data was recorded for 5 minutes and totally 20 minutes, for as there were four games, so in total 20 minutes recording was there. And for each subject 20 minutes recording is there. And now coming to the detailed experimental setup, actually here a subcomplex model already discussed by ma'am has been shown, where in the y-axis there is arousal, and in the x-axis there is valence. So actually, what is arousal? It is a state in which you feel excited or very alert, for example as a result of fear, stress, or anger. um, it can raise arousal. And valence actually refers to the pleasantness or unpleasantness of an emotional stimulus. So these are the very well known emotions we can consider. And in this experimental setup, all the subjects, that means whoever were playing the games, were given a self assessment mannequin. They were asked to fill this form up, and for that, gender, age, and do you have any neurological disturbances, like that, yes or no, two options were provided to that particular question. Then, have you played this game before? This was actually asked to know whether those subjects were having any experience, whether those specific games were new to those subjects or not. For that, this particular question was asked. Then the does this game remind you of any event in your memory? That was actually to select the right stimuli. Actually, it shows that if any event serves to be a reminder of something from the past to the subject's feelings will become more intense. So for that, this particular question was asked. And then for identifying the emotion after playing the games, they were asked such questions like, how satisfied are you with the game you are playing, how boring was the game you played, how horrible was the game you played, and how excited was the game you played, and how calm was the game you played. So satisfied, boring, horrible, calm, and excited, these are the five words which used to um, explain the game type or the emotions generated from those game playing. So these are the five words. And from that, four different games, as denoted by G1, G2, G3, and G4 respectively, were Slender, Unravel, Train Sim World, and Goat Simulator. The Train Sim World was actually boring, because actually this was rated as boring depending on the global scores, comments, and criticism. Actually, it is a simulation game, and it makes the gamers control the train. And they observed during the experimental that all of the subjects were bored with the game, since some technical information about the trains were necessary, which were not provided to the subjects. So only the experienced player who played previous versions of the game could understand the control mechanisms of the game. But the others, nearly all of them actually didn't understand the game, so just pushed some buttons randomly on the keyboard. So that actually resulted in low arousal and negative valence, and it was identified as belonging to boring genre. The next game was Unravel, that was belonging to the calm genre, because in this game subjects control the yarn that tries to fix the broken bonds of the people. And it's a relaxing game, since the kinds of music, sounds, and the atmosphere of the game were slow and relieving. So during the experiments, subjects understood the game mechanisms and they listened to the music of the game, so they felt calm and relaxed. So the classification level in this case was HANV, that is the high arousal and low, sorry, negative violence. And for the third game, it was denoted by G1 actually, that was Slender. It was a horror game. Why? Because the game was in the game, the players used to discover a house and many rooms in order to defect from the place. Players do not have any materials except a camera which shines on the dark places. Atmosphere looked to be very dark and sounds were very disruptive. So in that case, it was identified as the most difficult game, and in that case, horror type of emotion were generated, which resulted in high arousal and positive valence. And the last game, which was Goat Simulator, that was kind of funny game because players acted like a goat and performed some funny things including attacking houses, licking walls, jumping, etc. So for that, low arousal and positive valence were generated. Now coming to the code, for that we have to at first, I am using Google Colab over here. You can search for it in the Google with Google Colab, like, sorry. Yes, this is the link, collab.research.google.com. There you can go and sign in with your already existing Gmail account, so that there will be a option coming like open a new notebook. You can open a new notebook and you can name it with your whatever you are doing. You can name that particular notebook with that, and then this Python code comes, where the actually EEG, after collecting the EEG data, some steps are performed to process the data, and in this case the class levels will be HAPV, HANV, LAPV and LANV. So for 4 different games the class levels are 4 different ones, and for that actually we have to at first we have to import the numpy package, and we have given the nickname as np. That means in the code wherever we will want to use the numpy package, we can name it with np and it will be recognized as numpy. Then from the scipy.signal we have to import the ch1 and fric-z. These are actually specific to EEG, because actually not for only EEG, any for any signal processing task we have to actually at first remove the noise. The noise can be from the machine itself. That means in this case EEG can generate some noise. There can be noise due to some eye blinking like artifacts. There can be some noise due to in the circumstances also. So those noises have to be at first removed by proper filtering, and then the feature extraction takes place. For feature extraction also there are already existing feature extract feature extracting algorithm for EEG, and then classification according to your preferred model or according to your novel model, whatever you are proposing, that can be applied. So after that, import matplotlib, and from pyplot we have to import the PLT to plot any graph, or any, suppose I want to plot accuracy versus error graph, or TPR, that means true positive versus false positive graph. For that, if I want to plot something like that, I have to import this PLT, and after that pandas has been also imported, pandas package, and it has been nicknamed with PD. Now after that, EEG filters have been installed from the PIP package, and then I have to mount my Google Drive, so that the file residing in my Google Drive will be imported in my Google Colab notebook. So for that, these 2 lines are necessary: from google.colab import drive, and then drive.mount content of my drive will be mounted. and after this line the data set actually has to be imported. For that we can use the pd.read csv, that means the read csv method from the pd package, that is the pandas package, and after that I have to give the link of my dataset, whatever the folders inside the data set is loaded, so that link has to be provided inside this read csv function, and then frame is the pandas data frame from this dataset. That means this dataset has been actually collected from different time frames, whatever the duration is, so that has to be defined by the frame. And then we can see that the data set contains data from different lobes of our human brain: af3, af4, f3, f4, f7, f8, fc5, fc6, o1, o2, p7, p8, t7, t8. These are the human brain lobes, and various actually brain regions are there. And suppose someone has difficulty in seeing something, and someone has disorder in his or her eyes, so in that case the occipital lobe of the brain will be responsible for that. Someone suppose is having difficulty in hearing, or in auditory glands, they are having problems, so in that case parietal lobe will be responsible for that. So this frontal some electrodes from the frontal region, some electrodes from the prefrontal region, some electrodes from the occipital region, some electrodes from the parietal, some lobes are from the temporal channels. So all of the from all of the 14 channels the data has been collected, and then pd dot data frame, here the x is actually extracting the data into its frame format. And then if I just print the first 5 rows of that particular data, whatever the x is storing, so I can do that using x dot head comma sorry, inside the bracket 5. How many numbers of rows I can see, that will be the that will be provided inside the head function, and x dot head 5 will just show the 5 rows, first 5 rows of the data set. And here we can see a sample that minus values are there and plus values are there. These are the basically EG brain voltages, brain signal voltages in microvolt format. And then for the filtering purpose, this Seaborn package has been imported and nicknamed with SNS, and from the matplotlib pyplot this PLT has been imported, and then the we have to plot the figure from which the actually here we haven't applied any filtering method, just the raw data will be shown. The plot has been done for the AF4 lobe only, that AF4 electrode channel. The data looks like this, and after applying the Shiva-Shape filter, that is one well-known method. The other methods are Butterworth filters, bandpass filters. There are various other existing methods also for filtering. So for this particular work we have used the Shiva-Shape, and for that these actually are the packages, and their measurements, time, the sampling rate I have to measure also by dividing the measurements by time. And then if I print the sampling rate, then I can see that 288 is the sampling rate in this case. And Nyquist frequency, for the Nyquist frequency calculation part, sampling rate into 0.5 is the formula. And then I have to choose what are the means in which frequency range that particular EEG data is belonging to. So for that low cut and high cut, then the low value is calculated using a division of low cut by Nyquist, and high, that means the high value, that means the range. Actually we are finding the range of the filter. So if it is a band pass filter, then the low value and the high value will be calculated with low cut and high cut division by Nyquist. And then this is the formula of this is the code of just processing the filter with all of my columns in the data set. So this is done, and then after the filter, if I want to show the signal, that will be actually the this thing. That means before filtering it was the signal, and after filtering, if I see that it has little bit improved. That means the most relevant, without noise, the most relevant things have been already chosen. And after that, in this case, we actually used the convolutional neural network. Actually generally we have an idea that convolutional neural network for deep learning has is actually a classifier, but in our case we actually excluded the last layer, that was the that which was actually used for classification in conventional models. We just excluded the last layer, and we just included all the other layers. It depended on how the accuracy was coming, and we actually modeled with that. That means hyperparameter tuning was also done. So from here from the keras dot models, we actually had to import uh, some functions for sequential input, model, dense, dropout. This will be actually the layers of that particular convolutional neural network. Convolutional 1D, that is the one dimensional convolutional layer, two dimensional convolutional layer, max pooling 1D, that means the one dimensional max pooling, two dimensional max pooling. So all of the layers had to be at first imported in our work, then the batch normalization, then the leaky ReLU. So all of the modules at first was imported in our code, and then the as x actually was holding the all the values in data frame format. So actually for the x part, now we have to drop the outcome column, as this outcome column is actually having the class label. So we had to drop this outcome column, and axis equal to 1, it is actually showing that this drop function, drop operation will be done on columns. If axis value was 0, then that meant that the drop drop operation will be done on rows, but axis equal to 1 means dropping will be done using columns. So we have just supplied the outcome, that means the name of the column which we have to drop for the x, because the outcome will depend on the x values. That means the other 14 data from the from the 14 channels. So x is the independent variable over here, and there belonged the 14 channel data, and y was the outcome, that means the HAPV. In this case, as we are considering the subject 1 and game 1 data, so HAPV we already knew from the SAM, that was the user rating questionnaire. From that particular game, that means G1 was already identified as HAPV. So y, in the y, if the outcome had HAPV, then we only consider that as y value. And then the x train, x test, y train, and y test. These things are done actually for splitting the entire data set into two parts. One is the training. Already I hope you are familiar with the terms training and testing, and already it has been discussed by ma'am also. So we have divided the entire data set into two parts. The test size is considered over here is as 0.25. That means the 25% data of the entire data set were considered as test, and the rest of the 75% data were considered as training size. So that was it, and the entire data was split into two parts using this train test split function. And then we had to reshape the value as some more rows were shown, which couldn't be fit into the convolutional layer. So 28689, actually the total number of rows were divided into two parts, where 75% was this 28689, and the rest of the 25% that was used for the testing, actually those were actually those were actually 9563 rows. So here if I just print the x train 1 shape, then I can see 28689 14 and 1. That means 28689 rows, 14 columns. And x test 1 dot shape, if I print test, then I can see that 9563 rows, 14 columns. Now I have just considered epochs is equal to 20. As the number of epochs I have considered as 20, it can be varied according to your need. It can be 10, it can be 5, it can be 20, it can be 200 also if you need to train the classifier. So for that, the number of epochs in this particular work has been considered as 20, and number of classes, as we are just considering this S01 G1, that means the only data from a particular game, that is G1. So that G1 actually belong to HAPV class. G1 we already knew that this was a horror game, so it was belonging to HAPV class level. So number of classes was only one in this case. So we are considering just one game's data. And if you see the directory, there are S01, S02, S03, S4, S04, and up to S28, as 28 different subjects played games. So from all of them the data is present over there, and we are just considering S01. Yes, if I go to the pre-processed EEG data, then actually it is already noise removed. And if it is raw EEG data, actually I am working with that noise EEG data, so .csv format is that. And then S01 G1 all raw channels. Actually for this particular notebook I am using this particular thing, S01 G1. So subject 1 and game 1, so number of number of classes is 1. And then the model building part, here the first layer is sequential, and then convolutional 1D layer is added, then max pooling 1D layer is added, dropout layer is added, then convolutional 1D layer is added, leaky ReLU is added, max pooling 1D. So according to your need you can model it accordingly. So it is not fixed actually, and for this particular thing actually this model worked better, so we have considered it. You can compare with hyperparameter tunings also. There are already two automatic hyperparameter tuning functions present in the Python packages, random grid search. So you can use that, and you can otherwise use just manual values of hyperparameters like that. Here we have supplied the input shape of 14 comma 1, that means 14 rows 1 column. So like this the convolutional every for each and every layer we have to just mention the hyperparameter values. And after the model building part, if I just see the if I just want to see the model, then this summary function can be used for the model. So model dot summary, and then we can see that the convolutional 1D is the first layer. For that the output shape is this. The second layer comes as the max pooling 1D. For that the output shape is this. Like this the entire model can be seen. And then if I compile the model, so for that the compile is the function which can be applied. And then fitting part, so for the fit part, up to this no dataset was concerned. Up to this compile line no dataset was concerned. In general model was built, but in this line whatever we are doing is concerned with our dataset, because this x train 1 y train and this x test 1 and y test have been already defined previously for our particular dataset only. So X train 1, X train 1, X test, and then Y train 1, Y test. All of these portions are now already defined, and then we are fitting our model. This model we have already defined over there. Then we have seen the summary, and after that we have compiled the model. Then we are fitting our model into this X train 1, Y train, X test 1 and Y test. Here we have supplied the batch size, which can be varied according to the need. Here we have supplied the epochs. We actually already have given the number of epochs as 20, and the validation data, it means the testing parts of validation data. And then epoch by epoch, if I run this particular cell, then I can see that epoch by epoch the result is showing. And then uh, as already said, that for this particular task the CNN was used excluding its last layer, which was actually responsible for the classification part. In this work only up to feature extraction is done. So feature extraction, uh, we can do this feature extraction by just getting the weights from each and every layer of it, and those will be actually considered as the features of the particular data. And from those features, any simple model or anything you can run as a classifier, like SBM can be run, already discussed by ma'am, as BPNN also can be run. So anything you can run after this feature, after getting this feature vector. And for that, the np, that means the numpy dot set print options, this was the function. For that, np dot infinite, that means up to infinity times this np array will be considered. And here the print model dot get weights. So whatever the weights this model has generated, those has been printed. So this is particularly a feature vector. Up to this is particularly a feature vector. So after this feature vector extraction, any classifier can be fed into it and run accordingly. So if you have any doubt, you can ask me, and otherwise over to you, ma'am.
Yes, anything, any doubts are there? Okay, so we are moving to the next topic. So that is basically the how both of them techniques that we have discussed, one from the behavioral perspective, one from the psychological perspective, both can be combined to have a better human computer interactive algorithm. So for that, so it's basically we are going to deal with here the EEG sensors. So EEG sensors, how the EEG sensor works, we have discussed about theoretical concepts of EEG and the how the codes need to be run to get the features from the EG. Next, we are going to check how EG actually basically looks like. So here you can check over here this particular set of video of EG, that is the EG we have in our lab. Here you can check that Ahona is the subject over here. These are the EG signals that we are getting. This is basically the brain tech traveler acquisition system. This is the 21 electrodes are there. These are connected to the scalp. It is the non-invasive one, so that is the only in the scalp. Those are connected over here, and the subject is giving the EG. I'm just again running the particular setup as a very small video. That's why. So here you can check also there is a robot is there. So what we are going to do, we are going to instruct the robot from our brain signal. How that can be done, that we are going to discuss in this particular session. So how it will basically look like, how the robots can be run. Here you can check over here. This is the EEG sensor data that is acquisition is there in our laboratory, and based subject is giving the EEG over here, and there is a robot, that is the turtlebot 3 robot we have in our lab. That robot will be instructed to move forward, backward, or it will rotate left side or right side. What will be the applicability of that? Suppose there is a person with some disability, the person cannot move uh, by his or her legs. So we can generate a brain driven wheelchair system where the person is going to instruct the wheelchair where he wants to go, and how he is going to instruct the wheelchair by from his brain signals, like getting the processing the brain signals from that, uh, the wheelchair will be moved. So here the wheelchair is will, as we cannot procure the wheelchair due to some cost factor associated with it, so we have brought a very small substitute of that, that is the turtle bot 3 we have preferred. It is something like a mobile robot. It has two motors over there. Based on the two motor it can move forward backward, and here you can check the water bottle is placed above the turtlebot 3 robot, and based on the brain command the turtlebot 3 robot will bring the uh, uh, water bottle from one place to the place nearer to Ohana. Here you can check in that video over here. Ohana is commanding the robot by her brain commands, and based on that, where she wants to move the robot is coming. So there is some errors are there, our algorithm cannot properly detect, so it's moved in the rotated along the right side, that was the wrong thing. Then it's corrected itself, and so it's not like algorithm will going to give us 100% accuracy, there will be some glitches. So that was one of such glitch was there, but it finally takes the water bottle to Ohana. So if there is some person with disability was there who cannot bring the water bottle itself, so that person can have this type of robotic device installed in his or her home where the robot is going to assist. So this is the robotic application of using brain command. Another, we can check, there is another type of robot, that is the open manipulator X. It is something like our human hand. So our human hand, how it acts, so there are several joints in our human arm, like this is one joint, this elbow is another joint. So these type of joints are also present in the robotic arm. How we are going to grasp the different objects based on the two grippers are there. In here we have five grippers, but the robotic arm that we have procured, that is the comprising of two grippers. Here the robotic arm is being instructed to act according to the brain commands of the Ohana. So robot is acting like whether to grasp or not, to move forward, backward, based on the brain commands. Here you can check the robot is being instructed by the Ohana's brain signal, and it is moving accordingly. The EEG device captures the signals at the same time or simultaneously. It is being processed and it is being fed wirelessly to the robotic device, that is Open Manipulator X, to give a better human computer interactive algorithm. It is the grasping mechanism, this widening of arm mechanism, it is moving. So she is trying to move different joints one after one. So that's the application. Now there we have discussed about two different types of the robot. Now we are going to amalgamate these two robots to have a much more sophisticated HCI. Here, two robots, TurtleBot 3 and Open Manipulator X, both will be simultaneously controlled by the brain signal. Here, the Open Manipulator X has been given a water bottle. It is trying to grasp it by processing the brain signal. So we have to make the algorithm so much faster that there is a little amount of time delay is there. It will be placing the water bottle in the open TurtleBot 3. Here you can check the brain signals are capturing. At the same time, the brain maps are there, and so it is the completion of working of the Open Manipulator X. It has completed its work, and now Open Manipulator, after the Open Manipulator X, TurtleBot 3 take into account, and it now move forward to bring the water bottle to the subject. So here, first we are going to discuss about two different applications by this particular one. First is the EEG based gesture mimicking by an artificial limb using cascade correlation learning architecture. So What's the problem over here? That suppose there is a person with a disability, the person cannot bring the glass of water from a nearby table. So what we can suggest the subject, that if the person is having some difficulty in the arms, so we can give the prosthetic arm to that subject. So that prosthetic arm will be a robot who will act on the behalf of that subject to bring the glass of water to that person. That the videos we have already shown how we have implemented it, and so that was the final result of the implementation. Now we are going to discuss how that can be implemented in the coding. What's the solution of that? That we have proposed that there is a robotic arm that is going to grasp the glass based on the EEG command that is received from the occipital region of the subject. So person sees that particular subject, based on where it is looking, processing of that, it is bringing the glass of water. So this is basically the what we have proposed. What's the total setup of that? So there is a person, that is SA. Subject is going to throw a ball. Sorry. So there is a person SA, the person is going to throw a ball, and ST is the target subject that going to capture the ball. So the person that is going to throw the ball, that will be captured the gestures of that, like how he is throwing the ball, based on how he is throwing the ball, where the ball is going to be uh, reached after to the ST, like where in which direction I'm throwing the ball. Based on that, ball will be reached at different place. So if I can recognize from where I am throwing the ball and how I am throwing the ball, I the system will give the algorithm in such a fashion like it can understand where the ball will reach to me. Like the same way the cricketers play. If the bowler is throwing a ball, from the throwing of that ball, the cricketer process that. That's the human intelligence. The cricketers, that is the batsman, understand based on the bowler's gesture, like where the ball is going to land. So that's the human intelligence that we are going to transfer to that Jacko robot arm, where the robot will act on the behalf of the ST, and based on the gestures of the throwing person is going to understand the where the ball is going to land. So to understand the gesture of the throwing person, we have the kinect sensor that already discussed. From that kinect sensor skeleton is there, that feature is there, and that is being mapped with the already existing gestures. And then EG sensor is there for the person with the disability who cannot catch the ball. So if the person cannot catch the ball, there will be a prosthetic arm, that is the robotic arm is there, that is Jacko we have used over here, and the arm will going to capture the ball. So from that EEG signal, again feature extraction is there, that is going to be mapped using cascade correlation learning architecture. This is a type of neural network. And then how the robot arm need to be moved to catch the ball, that is the displacement calculation is there. So this is all about the training phase. After that, in the testing phase, what happens? Kinetic sensor is not there. By just throwing the ball, the based on the EEG, person is going to look at the ball where it is coming from. That occipital lobe, it's going to understand the where the ball is going to be landed. So based on that, feature extraction, displacement calculation and there, and then bypass network is there, that is going to instruct the robot where to catch. Why there is a bypass network? Suppose I am seeing that ball is coming in this direction. What I am going to do, I am going to see, so that's my occipital lobe is going to be activated. Then that is going to be processed in my brain. After that, my motor cortex is going to instruct to place my hand in such a fashion that I can capture the ball. But for this robotic arm, only the occipital lobe is there. I am seeing where the ball is there, and there is some disability with that subject arm. So this subject cannot capture the ball himself or herself. So it is going to be bypassed everything, and there is no concept of parietal lobe, and there is no concept of motor cortex lobe. Robotic arm will be instructed based on the bypass network, and robot arm will going to capture the ball. So that is basically over here the rehabilitative patient is there. So this is the testing phase that has been done. So why we have used the cascade correlation learning architecture? It's very it's not so much known architecture, but the algorithm is architecture is very much important over here. Why? That it begins with a minimum input output nodes, and gradually the network trains and add hidden layers to create a multi-layer neural network. And learning algorithm to install a hidden layer with a systematic sigmoidal activation function such that the residual error signal is minimized, which in turn maximizes the correlation between the new network sound. So this is the experimental setup we have. There is the kinet sensor, and this particular experiment has all done in the AI lab of the Jadavpur University, where I have done my research. This is the subject, this is the SA, and this is the subject, this is the ST. This is the EEG are placed in that subject that is being captured over here. You can check over this is the EEG device. This is the and the ball is thrown over here. Subject is catching is based on that. There is the different intermediate states of how the person catches the ball. So this is the initial state to the goal state. Now, what happens if it's a testing phase? There is no parietal or motor cortex, but only by seeing the ball where it is coming, the robotic arm will be instructed to catch the ball. Where this a rehabilitative patient is there, you can check the person is not moving his or his arm. He is just standing, but by just standing and he's just looking at the ball. Every time he's looking at the ball, this time also he's looking at the ball. So every time it is looking at the ball, based on that occipital region processing, the robot is capturing the particular ball. So in this EEG, we have here considered the power spectral density PSD feature for 11 instances. So from 11 direction, it can throw the ball. That was our algorithm. So 11 goal states were there. This the initial state was same, and but there can be different types. So 11 goal states are there. Each are represented in the kinet skeleton view. These are the design blocks of the cascade correlation learning architectures. How many input nodes are there? In 4 different CCLA are used, and how many output nodes are there? These are the performance analysis with the existing algorithms are over here. So that was one application. Next, we are moving the next application, that is the robot navigation for healthcare application. So before that, it is very much one-sided talk is going on. So any doubts or any discussion is there, it will be great to discuss with you. Any doubts of anything you have, please. Anything, any suggestions or anything that will motivate us as well, that what you find the lacuna of this particular research or anything, any doubts or any particular domain, or anywhere you feel like there's a new one, you want to also work on that particular domain, anything other than if that we can discuss, it will be great. Then we'll be moving for the next topic.
Participants, please respond if you have any query.
Okay, so we are moving to the next one where Ohana is basically working on, that is we have already discussed, that is the robot navigation for healthcare application. So, what's the objective of that? We are trying to develop a much more sophisticated brain computer interfacing device where the device, why the devices need to give the better rehabilitative interaction with the subject, such that seamless interaction between task and executing output device is there, and without any cognitive disruption. There are some approaches that are present in the existing literature, but what happens, the literature that are present that suffer from cost, time, and less accuracy. So what we are trying to do, we are trying to make a much more robust and reliable system, and much portability issues we have tried to solve over here. Uh, with and the system that we have tried to develop that is going to have less or no intervention of humans, and flexibility of time that is also taken into consideration. So these particular, that is the existing, some few literatures are existing in this particular domain over here. So BCI, this particular topic is very much well known in today, and it is growing rapidly. So it's a part of the HCI, human computer interaction, where humans are interacted using the brain signals that are falls into the BCI application domain. So it's going to give the ability to the disabled person to interact with the external environment. Uh, so person can have certain type of neurological disorders like amyotrophic lateral sclerosis, this brain stroke, those can be there. Apart from that, there can be like the conventional interfaces like the keyboard and mouse, whatever we are using today to instruct the computers to work on our behalf. Like if we can give the brain commands to the signal or to the system to write a email, or to do an, like in our brain we are thinking to, okay, so I need to call one particular person. Suppose I want to call Moporna ma'am, so I am thinking in my brain to call her. So if I just process that brain signal and automatically call can be made to her, that basically we are trying to done over here. So if a person that already discussed, if suffers with any type of prosthetic damage, we can give the aid to that subject in doing the day-to-day course by having some robotic assistance or some artificial limb. So the subject has wearing a EEG device. So there is a EEG acquisition device that is placed on the subject head. From the EEG acquisition device, EEG signals filtering is done for noise removal. Then classification of then basically from that, as already discussed by Ahona, we have done the channel selection, then feature extraction, and finally classification of motor imagery actions are there based on the robot's movement. So here the robot that already been shown in the real time, that is the open manipulator X is there, that is being worked on the if the subject is having disability in moving his or her arm, then we can give the prosthetic arm to that subject. So this is the national international status of that work. There are few works are there, but as already discussed, the works have lacuna in time, cost. And so what we are trying to do, we are trying to make a system where less amount of time and more efficient system we can give to the system. So we are trying to make the novelty and uniqueness in the optimal channel selection. Better feature extraction methods are trying to be done, and no better classifier will be there. So this is basically the EEG setup that is already been discussed. So based on that, different brain lobes are there. From different brain lobes, you already discussed, signals are being captured. These are the brain activation region of S loretta that can be checked from the S loretta. This is the different components of the open manipulator X, this particular one, and this is Ohona is there to instruct the open manipulator X. Here two say, screenshots of that particular video we have shown, that is there. Here you can check the video is playing. So there is a error is there. So it's very important to recognize your error, where you are getting the error. If we can recognize the error, we can justify the error. And every time we are seeing that Ohana is looking at that robot, so occipital region is working for her. So here you can check. So we have managed the error over here this time, and the robot can successfully bring the glass of water, here the water bottle, to the subject Ohana. So this is different topics we have discussed. So next we'll be discussing about, if you have any doubt, you can surely ask, or we can give a small introduction of how heart attack prediction or analysis can be done using Python and Google Colab. Uh, Anything you want to discuss? Okay, Ahuna.
Okay, if there is no doubt, then I'll be proceeding with our next work, that is used for heart attack analysis and prediction. Here is a very simple data set containing demographic data of different subjects. So for this,
Ma'am, I think we have one question
Yes, we
in
have
the chat
one. Yes,
box.
yes. So we have one that is how to search for good data set. So good or bad data set, that I cannot say. That you have to work on the data set, understand the data set, then you can say whether the data set is good or not. But in Kaggle, most of the data set actually the work has been started. Actually, Ohana started working just before the pandemic, so that time we cannot collect the data from our lab. So we have to only trust on the Kaggle dataset or the dataset that are available freely downloadable. There are other BNCI available datasets are there. Other datasets are as well there. So based on the dataset we have worked on. So what you are trying, what particular work you try to do, search that corresponding keyword, use that corresponding keyword, you can get the dataset. Whether the dataset is good or not, if that was your question, so you have to understand the data. That requires much more experience. If you have a high amount of experience, then only you can say whether the dataset is good or not. Yes, so Ahona, you can start.
okay. For heart attack analysis and prediction, the dataset contains different attributes like age, sex, EXANG, CA, CP, TRTBPS, COL, FBS, REST ECG, thalach, and target. What are they? Age is the age of the patient, sex is the sex of the patient.
Ahona, you haven't started screen sharing.
Oh, sorry. Yes. Is it now visible, ma'am?
Yes, it's visible. Please
Okay.
continue.
For heart attack analysis and prediction dataset, we are again considering a dataset from Kaggle, where the age, sex, and then EXANG, it is actually the exercise induced angina is over there or not. If it is present over there, then the value will be 1, and if it is not present, then 0 will be the value. For CA, it is the number of major vessels that will be ranging from 0 to 3, and for the CP, it is actually the chest pain type, whether the patient is having any chest pain, and if it is having chest pain, then the type of it, if it is containing the value 1, then that means that there is typical angina. If it is containing value 2, then it is showing atypical angina. Then it is if it is showing 3, then that means non-anginal pain. If the CP value is 4, then it is asymptomatic angina or asymptomatic pain. So after that, the next attribute comes as TRT BPS, that is the resting blood pressure in millimeter of mercury. Then col is the cholesterol value, that is in milligram per deciliter, fetched via BMI sensor. Then the FBS, that is the fasting blood sugar. If it is greater than 120 milligram per deciliter, then it is 1, that means the value of this FBS attribute will be 1, and if it is less than 120 milligram per deciliter, then it will be 0, that means false. Next comes the rest ECG attribute, where the resting electrocardiographic results are there. If the value is 0, then that means it is normal. If the value is 1, then that means it is having that means the patient is having STT wave abnormality. And if the value is 2, then it is showing probable or definite left ventricular hypertrophy by Estes criteria. And the next attribute is the thalach, that is the maximum heart rate achieved. And then target, that means that is the class level. um, Based on these features, the target will be attempted to be find out. So if it is 0, that means the less chance of heart attack the patient is having, and if it is 1, that means more chance of heart attack. So for this, again, like the previous example, NumPy, Matplotlib, and Pandas have been imported in our code. And then for the trend test split purpose, that means in this case also the entire dataset has to be split into two parts for the training and testing. So for that, sklearn and model selection, we have to import the train test split, and then from sklearn we have to import the svm, as we will be using svm, that means the support vector machine classifier in this case for classification. So svm has been imported from sklearn. Now the importing dataset part. So data equal to pd.read csv, and again the link of the dataset wherever the dataset is stored in my google drive. So content my drive, my drive, and then hard.csv. So this hard.csv is the file name of the dataset. So data is loaded in this line, and then x and y splitting. For that age, sex, cp, trt, bps, whatever the parameters already have been discussed. For that the x is that means x is concerned with the independent values. For that the attribute names and then dot values, so that it can contain the values of this age, sex, cp, whatever the values are there for different patients, that will be held by the x, and y will be actually storing the output values. That means the last column, it is the output, that means 0 or 1, already discussed. 0 is less chance of heart attack, and 1 is more chance of heart attack. So for that um, y has been denoted, which is actually storing the class levels. Now if I print the x, then x train, that means this is the train test split part. So actually this one is kept as comment, so you can ignore this. Going to this, it is the training test splitting part. So here also we have considered the test size as 0.25 of the entire dataset. So if the entire dataset is represented with 1, then the test size is 0.25. That means the 25% of the entire dataset is the testing dataset, and 75% of the entire dataset is considered as the training dataset. So like this, the previous example, all the variables in this case also have been um, defined. And then the model building part. Here I have considered kernel as linear. You can go through any literature regarding svm. You can come to know that there are different parameters for svm. One is the kernel, one is the gamma, one is the c. You can go through their working mechanisms, what what are the things depend on those parameters. Those will be also known by you if you go through any literature on svm. So actually svm.svc, svc is the sv classifier, that means a support vector classifier, and the function is called. And for that model building, we are just supplying the values of the parameters. For this particular model, linear kernel has been considered, scale value of gamma has been considered, and c has been considered as 1. But these values can be varied, as in my case actually I will be also showing the results by varying this gamma and c also. And after that, after defining all the values of parameters, I have to just fit the model using x train and y train. That means x train, in the x train there will be the training portions, age, sex, cp, whatever is there in the training portion, those portions, these attribute values will be the x train, and whatever is there in the training portion, those portions output values will be the y train. So dot fit, and then x train, y train, these two arguments have to be passed into the fit function. And then ypred is the linear model. I have named it with linear model, as the kernel is linear, that is why I have named. You can name it otherwise also according to your preference. So linear model dot predict x test. That means using this x train and y train, I need to predict the y test value. So for that, ypred is considered as the variable name, and then x test, based on this x test, this ypred, that means the prediction will be done. That means whatever the patient is having less chance of heart attack or more chance of heart attack, that can be predicted using this predict function. And then if I want to see the accuracy in case of my linear model, then I can see that I just want to store my accuracy value, whatever this score function will return. I just want to store that particular value into the accuracy linear train, accuracy underscore linear underscore train variable. So I have named it in that way, and then the model name, then dot score, and then x train y train, that means the accuracy of training I am showing. And this particular model is showing 0.85333 accuracy, that means 85.333 accuracy. And if I want to see the accuracy of testing phase, then I can see that the linear model dot score my same, in the same way I just want to test the accuracy of testing phase. So linear model dot score, then here the train values were passed, x train and y train. Here the test values will be passed, x test and y test. After that, if I just print the accuracy linear test, I can see there is 0.8 testing accuracy, that means the 80% training accuracy. And if I want to just print the classification report using confusion matrix, then for that I have to import the classification report and then confusion matrix for visualization, the tree, and then linear pred for the linear model predict x test. I just have printed the classification report. So the precision recall F1 score, as already discussed by ma'am, these are the performance metrics for a particular classification task, and the support values already have been shown over here. Now if I want to plot the region of sorry ROC curve actually, then
Receiver operating
yeah,
characteristics.
receiver operating characteristic curve, then this is the function of receiver operating characteristic curve. And then for this, if I just want to plot that, then from scalar matrix I can import also ROC curve and area under the receiver operating curves, that is the AUC value, that can also be found out using this AUC. So importing the plot again, it actually can be commented out, as I have already um, used, as I have already imported this PLT in the first cell itself, so it can be commented out. And if it is there also won't be any problem. And it was the model name was linear model, so linear model dot predict prob a, then x test. So probability, and after that false positive rate, true positive rate, and thresholds. From this from this ROC curve of y test and probes, we can find out these three values. And using this FPER, that means the false positive rate and true positive rate, if I plot that into the x and y axis respectively, then the plot ROC that is the plot ROC curve function, inside these two variables are there, we can see that the receiver operating characteristic curve for this particular linear MDL, that is my model for SVM using linear kernel. So this is the ROC curve. And if I want to print the AUC score, for that I can use matrix dot ROC underscore AUC score, and I can just pass two variables inside it, y test and probes, and using that print AUC can be done. So the value AUC is storing now is 80.8314. So this is the AUC for this particular model. Now the confusion matrix can be shown with this particular thing. Various axes are defined with this. Next I have done the same thing using kernel, using sigmoid kernel. So here sig is the model name, as in the previous case the model name was linear underscore MDL. Here I have just used the sig uh, as the model name, and here I have varied the kernel, that is the sigmoid kernel I have used over here. And C value has been 1. Decision function you can use anything, and for that the accuracy has been, for the test purpose the accuracy has reduced. We can see that for the test purpose x test and y test, if these are the two values, then I can see that 0.5466 is the accuracy. So by varying the hyperparameter values, the accuracy can be varied widely. So it was in the previous case the testing accuracy was 80%, and in this case it has reduced it to 54.66. So a wide change in the accuracy if I have changed the kernel. For this particular model, linear is fitting more accurately, but for some another data set, for some another model, the sigmoid can be more effective also. So that depends on the model and the data set. So you can experiment with that. And some already discussed models are there. Some already here, so I have mention these things manually, but randomized search and auto grid search are there. So you can experiment with that also. Two functions of automatic hyperparameter tuning available in the Python library. So that also you can use, and you can see whatever the changes are coming, whether it is good, that means whether it is improving the performance or it is decreasing. So a concept can be generated. Is there any doubt or anything?
Uh, yes. So that was how heart attack analysis and prediction can be done using Python, where a data set that has been downloaded from the Kaggle, and that is being features from the after feature extraction classification has been done using SVM. So in today's lecture, we have discussed about different domains of the healthcare, from the kinetic data, from the image processing, from the easy data, as well as then the heart attack analysis and prediction was there. How health, not only that the software part of only the coding, how that can be implemented in the hardware, like different robots can be implemented to give a proper support to the human being, that was also there. And so this we have in the conclusory part of this particular session. So like if you find this particular discussion helpful to you, or if you want to go much more deeper on this particular domain, so this is my Google Scholar account. You can find out my latest publications. You can go and find that one from this Google Scholar account, as well as there is a YouTube link where you can find out different videos that are present, where you better understanding of my research that can be done over here. And with this, I am thanking you to Moparna ma'am for giving me this opportunity to interact with you all. It was a nice way of having this one. Thank you so much ma'am for giving me this opportunity, and thank you to you all for listening. I hope I am not that much boring to you all, as I did not get any queries from you. So anyway, ma'am, over to you.
Thank you, ma'am. It was a very informative session. We have got to know about the different aspects of healthcare, the applications of artificial intelligence in the healthcare sector, as well as we have got a clear knowledge regarding the various hands-on issues on all the various problems of healthcare that are it is a very what I say, it is a very important topic, and about all of us are really concerned. So it will be better if many of the things can be implemented through artificial intelligence in the healthcare sector. Mm. So if anybody has any queries, you can ask, or otherwise, we will call it for this day. And the announcement for tomorrow, that in order to get the certificate, you have to attend the assessment test as well. After that, there will be a short session on research methodology by Dr. Shamajit Kaur, Professor, Department of Mathematics, NIT Durgapur. And after that, at the end of this session, final feedback link will be shared to all of you. So, in order to get the certificate, the final feedback link that will be shared tomorrow at the end of the session, as well as the assessment test, has to be given. The exam timing is 2:30 p.m. Instead of 2 p.m. So the session will start at 2:30 p.m. tomorrow. The link for the assessment test will be given in the chat box. So all of you, if you have any queries, so it will be posted in the WhatsApp group as well. Okay. So if you have any queries, you can ask. Okay, so today's feedback link. So today's feedback link is already posted in the chat box. Kindly give your attendance for today's link. Ma'am, there is one question in the chat box regarding mental health data. So
Uh,
Sumit Singha has written that I am working, but sometimes it is very tough to find.
Tough to find mental data, is that was your question? Uh, Yes, okay. So data set, first of all, you can got from Kaggle. There was also a very good data set by BNCI. That data set was there. And obviously, the last one that I can say that best to get the data in your own lab. So if you can arrange any sort of grant or anything, you can procure the instrument and you can collect the data. Like what type of work you want to do. It's many times for any type of work. What you are actually trying to do, exact sort of data you might not able to find in the internet. So for that, you can or you can go for any collaborative research as well.
So participants, please fill up the feedback link for today, and please join the session positively tomorrow at 2:30 p.m. for the assessment test, and followed for which there